So we haven't had an introduction yesterday to how do we think about flux integrals, integrals of vector fields that measure the extent to which the field crosses across the path that we're taking rather than aligns with the path that we're taking. And so that little 90-degree change of perspective takes us from circulation integrals into flux integrals. And so we can use those to measure to what extent is a vector field flowing into a region or flowing out of a region. Do we have sinks and sources for that vector field, or is there always as much inflow as there is outflow? And so we developed that as a macroscopic idea of a flux integral, and then we developed its microscopic counterpart, the flux density, as a particular type of derivative of a vector field. That derivative was the divergence of a vector field. So just to remind us about what those relationships were, we had this idea about the total flux of a vector field as being the integral of the scalar cross product of a vector field with a unit vector that faces in the direction of the parameterized curve. And then the flux density was that flux divided by the area that's bounded by the closed curve that we're integrating over. And in the limit, as that area shrinks down to 0, we get this quantity called the divergence, which is the x partial derivative of the x component added to the y partial derivative of the y component of our vector field. And those two are related together by a Green's theorem-like result that you discovered, that this flux through a closed curve in 2 dimensions is the same thing numerically as the double integral of the flux density of that vector field on the region that's bounded by that closed curve. And so this is an instance of what we call the divergence theorem. And so one of our goals for today is going to be to get some more practice using the divergence theorem, applying the divergence theorem, not just in 2 dimensions, but also in a 3-dimensional context. And in a 3-dimensional context, applying the divergence theorem means finding the flux not through a curve, but through a 2-dimensional surface. Right? And so that's going to be our conceptual leap that we make today, is what do we have to kind of do differently, and how do we have to kind of think differently if we want to think about flux integrals in 3-dimensional space where that flux is fluxing across a 2-dimensional surface. So when my 2-dimensional surface is a closed surface, like in the very last example in the activities from yesterday, it was a cube, so all 6 faces, which form the outside of a unit cube, that forms a closed surface, right? It divides 3 space into an inside and an outside, right? And that's what we mean by a closed surface. Closed surface does that uniquely. And so when I have a closed surface, we can use this approach that you used here at the end of the activity to find the flux either into or out of, depending on the sign, that closed surface by replacing that flux with a flux density, in other words, the divergence, which in the 3-dimensional case, we just have a z component in addition to the x and y, and the derivative happens the same way, the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. And then using a triple integral to integrate that flux density over the interior of our closed surface, which is now a bounded 3-dimensional region inside of 3 space. And so that's a 3-dimensional invocation of the divergence theorem, and it gives us the flux through that closed surface, the outward flux from that closed surface, depending on the sign. So the 3-dimensional divergence theorem is one tool that we have then for computing the flux integral through a closed surface. And in fact, anytime we are doing a flux integral through a closed surface, the divergence theorem is an option. And it's kind of a way of trading that surface integral for a triple integral over a volume in 3-dimensional space. So this is analogous to what we did with circulation, where when we were thinking about computing circulation around a closed curve in 2-dimensional space, we had these 2 different sort of cases that we could consider. One case is if we just so happen to have a path-independent vector field, then finding the circulation, we have this fundamental theorem that we could use. There's not going to be a fundamental theorem analog for us for surface integrals. We could probably come up with one, but it would be pretty contrived, and so it wouldn't be very useful broadly. And so it's more the right-hand side of this diagram that we're going to have a correlate to when we talk about surface integrals. That if we have when we had a simple closed curve, we had a theorem, Green's theorem, that helped us to evaluate the circulation around that simple closed curve. And so similarly, when we think about surface integrals, if I have a simple closed surface, then that will help us to evaluate the flux through that surface by trading it out with a triple integral, and that's the divergence theorem. But there is going to be a third way, a third theorem that we're going to be able to get some exposure and some practice using today. And that's the theorem that we can use in this other case where I might not have a closed surface. If I have a surface that has a boundary on it, then the boundary of that surface is going to be a curve in three-dimensional space. And so I could, if I wanted to, in principle, define the circulation of a vector field around that curve, which is the boundary of my piece of open surface. And there's a wonderful theorem called Stokes Theorem, which is going to give us a relationship there. So if we were to sort of write out what is the decision calculus, how do all these different theorems fit together, I'm going to try to do that here so that we can get the 40,000 foot view before we start to descend through the clouds, and then probably not going to really land until tomorrow when we do some of these surface integrals by hand, but at least we can get to a lower altitude. So what does it look like from 40,000 feet? So of the two types of integrals that we're interested about, we have line integrals and we have flux integrals. Line integrals are taken along a curve in 3 dimensions. Flux integrals are taken on some patch of surface in 3 dimensions. And in the case of line integrals, we're interested in how the field flows in the same direction as the curve. So we're taking this dot product with this tangent vector dr. And for flux integrals, we're interested in how the vector field crosses through a surface rather than along a surface, and so we're taking a dot product with a unit normal vector to that surface, which is perpendicular to the surface. So that's the qualitative difference between these two types of integrals. And so what the theorems do, that I'm collectively calling the Stokes theorems in 3 dimensions, is that they help us to translate in between these two worlds and give us options. For instead of evaluating one of these integrals directly as it's written, we can trade it out for a different type of integral that very often is much easier to evaluate. So the first such example is, what would I do if I have a closed curve that I'm taking a line integral over in 3 dimensions? In the 2-dimensional case, the answer was Green's theorem. And as we're going to see in a few minutes, Green's theorem in 2 dimensions is just the 2-dimensional flourish of a 3-dimensional result that's called Stokes theorem. And so Stokes theorem tells me that I can trade out the line integral of a function along a path in 3 dimensions for a surface integral on the surface which is bounded by my closed curve. So if I have a closed curve in 3 dimensions, there is some patch of surface that has that closed curve as its boundary. And so I can take an integral on that surface. But what would I be integrating? I should be integrating some form of circulation density, just like in Green's theorem. The problem is that where in 2 dimensions with Green's theorem, the circulation density is a scalar quantity, because either we're circulating counterclockwise or we're circulating clockwise, and those are the only options that we have. But in 3 dimensions, we're circulating with some amount of speed, so there's a strength of circulation, which is a scalar quantity, but then there's also a direction of circulation in 3 dimensions that could be sort of any point in a sort of 2-dimensional sphere. Any direction in a 2-dimensional sphere could be my direction of rotation, right? And so the circulation density in a 3-dimensional vector field can't be a scalar quantity anymore. It has to have both a magnitude and a direction to tell me what is the direction of the circulation at each point. And so instead of a scalar product, we end up with a vector product that describes for us the circulation density of a 3-dimensional vector field. That derivative is called the curl of a vector field, and it's nothing more than the vector cross product of the derivative operator with my function, with my vector field. So we think of this as the vectorial circulation density, if you like. So this is one translation that we can do. If we have a line integral on a closed curve in 3 dimensions that we would prefer to evaluate in a different way, Stokes theorem lets us recast it as a surface integral on the patch of surface that has that curve as its boundary. Meanwhile, if I have a flux integral that's on a closed surface, we have the divergence theorem that comes in and lets us trade that out for a triple integral on the solid region in 3-dimensional space that's being bounded by my closed surface. And what I'm integrating in that case is this function, the divergence. It's a scalar function that tells us the flux density of the vector field. So divergence theorem, we trade out a surface integral on a closed surface for a volume integral, a triple integral on a solid region. And the last connection to make on this diagram is that I have a surface integral here and a surface integral there. Right? If I can match those two things up somehow, then I can also run Stokes theorem in reverse. Right? If I, for some reason, know that my flux integral is the integral of the curl of something, right? If f is equal to the curl of something, then that means that my flux integral can be interpreted as this right-hand side of Stokes theorem, and I can reconvert it back into the left-hand side of Stokes theorem and convert my flux integral into a line integral on a closed curve. And that is always a good trade when it's possible to make, because line integrals are the simplest version of what we're trying to do. So that's the sort of agenda that we have for how these pieces are all going to fit together from 40,000 feet.